Welcome back, everyone. We're now in the second part of Lecture 2.7. Here we're going to discuss non-vertical and non-horizontal asymptotes to the graph of a rational function. We call these asymptotes oblique asymptotes. Let's look at the definition. The line y equals mx plus b, m non-zero, is an oblique asymptote of the graph of f if at least one of the following is true. The first one is if the limit of f of x minus the quantity mx plus b as x approaches infinity equal to 0. What does this limit mean? This limit means that as x goes bigger and bigger indefinitely, or that is x approaches infinity, the distance of your function, which is f of x, and the line, which is y equals mx plus b, their distance, or their difference, f of x minus mx plus b, gets smaller and smaller, so that means the limit is equal to 0. Okay? In the graph, that means when the function goes to the right indefinitely, the function gets nearer and nearer to the line y equals mx plus b, as shown in these four graphs or illustrations. So the four illustrations shows four possibilities in how the limit as x approaches infinity of f of x minus mx plus b is equal to 0, or that is, the line and the graph gets nearer and nearer to each other. Nice! Another thing is if the limit as x approaches negative infinity of f of x minus the quantity mx plus b equal to 0. So this is similar, but in this case, x gets smaller and smaller, or we are looking at the function going to the left indefinitely, as shown in the following diagram. So as the function goes to the left, it gets nearer and nearer, or becomes asymptotic to the line y equals mx plus b. Great! Now we know the definition of oblique asymptote. Let's look at an example of how to find an oblique asymptote to a rational function. Let us consider the rational function x cubed plus 4x squared minus 5 all over x squared minus 1. Note that this is the same example we did in the last video. The first step in finding oblique asymptote is to divide the numerator by the denominator using long division as shown. So please verify that the quotient is x plus 4 and the remainder is x minus 1. Because of this, we can now write f of x as x plus 4, the quotient, plus the remainder x minus 1 all over x squared minus 1. This is actually how we want our rational function to be written, because if f of x is written this way, we know that the candidate oblique asymptote will be the one here, or that is the quotient y equals x plus 4. To verify this, if you put x plus 4 on the other side, so that is f of x minus x plus 4, quantity x plus 4, which is equal to x minus 1 all over x squared minus 1, this is actually the f of x minus mx plus b as written in the definition. Hence, to check or to verify that indeed it is an oblique asymptote, we only need to check whether the limit of this goes to 0 as x approaches infinity. And indeed, if we take the limit as x approaches plus or minus infinity of x minus 1 all over x squared minus 1, we should get 0. This verifies that the oblique asymptote is y equals x plus 4. Very nice. Okay? So actually, if you notice, whenever you have a rational function p of x over qx, if q of x is not a factor of p of x, you can always have an oblique asymptote if the degree of the numerator p is 1 more than the degree of the denominator. So again, if the denominator is not a factor of the numerator, and the numerator has degree 1 more than the degree of the denominator, then you will always have a linear oblique asymptote. Okay? Great thing to remember. Now, before I move on, let's answer the following questions on asymptotes. Okay? Can or may the graph of a function and its asymptote intersect? What do you think? The correct answer is yes. Okay? It can happen that the function or the graph of the function and its asymptote intersect, as the following example show. So here is a function that intersects its vertical asymptote. Here is a function that intersects its oblique asymptotes. So actually, your function is asymptotic to this line. So again, gets nearer and nearer as x approaches positive infinity in this case, or gets nearer and nearer to the oblique asymptote as x approaches negative infinity. But the function intersects the asymptote. Okay? For horizontal asymptote, it also can intersect or may intersect as shown in this graph. Okay, so you have a horizontal asymptote here, horizontal line there, but the graph of the function intersect the asymptote. Okay, so again, the graph of a function may intersect its asymptotes. Great, that ends this part of the lecture. In the next video, we will be graphing functions with asymptotes. So we are now ready to graph rational functions, combining all those concepts that we know of relative extrema, concavity, table of signs of the first and the second derivative, and asymptotes. Alright, see you in the next video.